My name is Morten Breinholt Jensen, and I'm head of innovation department in NOAH. And I have been asked to talk about our R&D projects on fly ash. 4 topics I want to talk about today. I would give just a brief background on our current technology, what we do at Langøya. Then we will move on to our concept called resalt, which is recycling of salts. Then I will talk about a concept we have called Carbonate, which is carbonation of fly ash, where we use fly ash as a CO2 sink and also can treat fly ash. And finally, I have one slide on valorization of fly ash, where I want to discuss, at least present and discuss some possibilities, but also maybe some challenges using fly ash as a raw material into other industries. I assume most of you have seen this slide before, but let's go through it again, just to give you a background. Our philosophy in NOAH is to use waste to treat another waste, so we don't purchase a lot of chemicals. The only chemicals we buy in is for the water treatment. The rest is actually waste material. And our 2 main waste streams are acid, which is sulfuric acid, which is a waste product from Kronos Titan in Fredrikstad, where they produce titanium oxide, which is a pigment, white pigment. And after this process, we get sulfuric acid, and the concentration is around 25%. And in numbers, we're talking about 200,000 cubes per year, so it's quite a lot of acid. The other big waste stream is fly ash. We receive approximately 300,000 tons of fly ash each year. And the alkaline acid ratio here is almost in balance. The fly ash here is slurified with water and pumped into our neutralization plant, where we mix it with our sulfuric acid. And out of it, you get precipitation of gypsum. And also into this neutralization plant, we can add other kind of industrial waste. And this could be in wastewater, other kind of acids, and also alkaline material, as slurries. After the neutralization plant, it's a slurry, we call it gypsum slurry. It's pumped into our landfill, and the solids settles, and excess water is either going through our water treatment system, where it's cleaned and pumped to sea, or is pumped back into our fly ash slurification process. So this is our current process at Langøya. When we're talking about salt, the process will be very similar up to gypsum slurry, but there is a necessity to implement a press filter, so we can separate the brine from the filter cake. And now we are doing a feasibility study to invest and implement a press filter at Langøya. Just a few words about the filter cake, because this is the filter cake. We have done a lot of tests. The leaching is very, very low. And hopefully this can be a product in the future. I'll come back to that on the last slide. The other good part about this is that the volume occupation of this filter cake is much less compared to gypsum slurry. So we can increase the lifetime on Langøya considerably. Well, the other stream out of the press filter is brine, obviously, and this brine will go into a process plant where we have to clean it before it goes into a recycling plant. And the main challenge is sulfate, because we don't want sulfate to co-precipitate with the other salts. The metal content is very, very low because this process is very, very robust. So the brine, clean brine, will go into a recycling plant to recycle the chloride salts. The sludge here can either be recovered or go into a landfill. When it comes to salt recovery, we are now in the phase of building a pilot plant. This is a 3-year project. So the total budget has been, or is around 30 million NOK. And the main goal is to verify if we can meet the industry standards of pure sodium, potassium, and calcium chloride. That's our goal, because we want to make industry products out of this. We have divided the project into 3 phases. The first is to make as concentrated brine as possible after the press filter, because our technology is based on evaporation. So if you have a very concentrated brine, the less water we have to evaporate and less energy we have to put into the system. So this is a really important step. The next one is cleaning the brine before it enter the crystallization plant. Heavy metals, since we can control the pH of our gypsum and our brine, the heavy metal content is very low. But as you may know, been working with fly ash, you have a lot of sulfate in it, and the solubility is fairly high. So we are now working on how to reduce the sulfate concentration and at what level needed, which is the targets. We don't know yet. Project plan. I think the most interesting part here is that we are now getting the pieces for the crystallization plant to Norway. All the pieces will be in place in November this year, and we will start erection of the pilot plant in the beginning of 2021. And it will be located at Herøya Industripark in Porsgrunn. Approximately 2 months of erection, and then we will do test running the rest of 2021. Maybe a bit longer, it depends. Meanwhile, we have to evaluate the technology, and the goal is to make a decision on whether we invest in a full-scale plant or not in beginning in 2023. This is the technical part. We also have a commercial part, obviously, here. This is potential partners in a salt recycling, let's say, economy. Just need to. Our main input. This is our. It represents our salt factory in the future, full-scale salt factory. The main input of salts obviously will be from fly ash, from Norway, Sweden, and Denmark. And the input will be calculated between 600 and 800,000 cubes per year, with a salt content in between 10 and 50%. And the total output just based on fly ash is in the range of 80,000 tons per year. And that is spread over sodium, potassium, and calcium chloride. To make the economy a bit more robust, we are also looking at other waste material containing salt. So we are looking into that now. So this is the market part of this project. But at least we think we can produce 80,000 tons of chloride salts separated. As I told you before, this technology is based on evaporation. You can regain most of the energy in evaporation technology, but still you have a boiling point increase, so we need some energy. And we are in contact with the Herøya Industripark to see if they have excess energy we can buy at a lower cost compared to using electricity. We have been discussing with a lot of potential customers, and Yara obviously could be a customer. They produce fertilizer, and potassium chloride is a valuable product. So this should be possible to send this potassium chloride to Yara. Calcium chloride, maybe a bit more tricky. We are not sure yet if we want to make it dry or in a solution. but still we believe we can get a fair amount of price for the calcium chloride and as a product. Also in the same area as Herøya Industripark, you have Innovin. They produce PVC, and they uses a lot of sodium chloride. So we've also been in contact with them and to see if they can be a customer of our sodium chloride salt. That is the salt. Then I move on to what we call Carbonate. Accelerated carbonation of fly ash is an extremely effective method of reducing leaching in fly ash. And because now we are using sulfuric acid to stabilize fly ash, but you can also use HCl or CO2. The mechanisms are more or less the same. And this process is based on that you can use flue gas from any kind of incineration as a source of CO2. So this process can be located in the vicinity of any flue gas emission point. So it's very flexible in that sense. And what is also important to us is that we can combine the carbonation of fly ash with salt recovery, because we can stabilize the fly ash first and then recover the salt later on. Always when we look at processes, we do life cycle analysis, and we also done that for the salt project, and it looks very good. This process is also overall CO2 negative. It means that we can capture more CO2 than we emit, including transport and the energy amount of the process. So it's a permanent capture of CO2. At Langøya, we have a big, large test center where we do a lot of things. When it comes to CO2 process, we have two processes we're looking at. To the left here, we have what we call the dry fly ash. It's actually moist. We add some water to the fly ash and then mix it with flue gas. We can mimic flue gas at Langøya. We have a small incineration plant where we use wood for making CO2. And this is a very, very fast process. The kinetics in moist fly ash combined with CO2 is very fast. And here we have a picture where you can see carbonated fly ash. The positive side also here, you don't need a lot of water cleaning because you just add enough water to make the fly ash moist. So it's a dry process and fairly simple. To the right here, we have another process where we do the carbonation in a slurry. The kinetics in the slurry is much slower, but we have invented a system where we make a huge area of the bubbles such that at least the kinetics of the carbonation is acceptable. Here, obviously, we have to clean a lot of water, but the good part is that we can separate the salts from the carbonated fly ash just with a press filter. So it's easy to combine with our salt project. Just give you some numbers on leaching. I've selected some species for fly ash, which we believe is important. This is raw fly ash before treatment. As you can see, lead, zinc are over the limit for hazardous waste disposal. Sometimes it's much higher. But after carbonation, we see that the levels are very low when we are down to inert material or inert waste. So the leaching is reduced dramatically after carbonation if you do it correctly. The other favorable thing by using doing carbonation of fly ash is that you produce a lot of calcium carbonate. And if you have calcium carbonate in water, you will see that the pH is between 9.2, 9.5, and it's and you have a lot of buffer effect. And just, I know this is very simplified, but still it represents actually what we observe. For lead, zinc, and copper, which is the main problems for fly ash, the minimum leaching of their hydroxides is at around 9 and 10, which is spot on what you get when you add the calcium carbonates in the water. So in that way, it's a very robust system that you will have long time control of the pH over long periods of time. So it's a very robust system. Then I have the final slide here where I will talk about waste valorization, which is the topic of this conference. For our main raw materials are obviously fly ash, gypsum, which is a combination of sulfuric acid and fly ash, and our waste sulfuric acid. Obviously, we have also been looking into zinc recovery because we have a lot of acid. The problem is that 99% of our acids we receive is sulfuric acid, and the solubility of zinc and lead and other heavy metals are very low with sulfuric acid because the sulfate concentration will be very high and suppress the solubility. So HCl obviously is much better acid to use to leach out heavy metals, but we don't have HCl. So for us, it's not that easy to see how we can develop a zinc recovery process based on the waste streams we have now. Cement industry, we also have been looking into that and have a great dialogue with them. This is maybe my view, but this is a fairly conservative and regulated industry, and it's completely understandable because they deliver cement for buildings that should stand for 100 years, so you don't gamble what you put into the cement. The feedback we get when we talk to the cement industry is that the fly ash has way too high concentrations of calcium sulfate, chlorides, and heavy metals. And obviously, you can remove the chlorides, but still you have the heavy metals and the sulfate. And I think the next question we should ask ourselves, should our fly ash from municipal solid waste industry be used as cement replacement or raw material in clinker production? Because I strongly believe you cannot compare our fly ash with the fly ash from coal combustion. It's two different products. When it comes to gypsum, which is a mixture of sulfuric acid and fly ash, we have been in contact with the concrete industry. It could be used as a fill material. They are quite optimistic, but we need to document that the leaching is very low over time. And you shouldn't start making high quality blocks with our gypsum because again, you have when they sell paving stones, it should last for maybe 30 years. So I think we should start in small scales, making paving stone, concrete blocks, and so on for industrial areas where we have control of your waste. The next thing is the cement industry. Gypsum is added as a retarder to slow down the hardening of cement. But again, the feedback is that our calcium sulfate content in our gypsum is low compared to the industry standards. And we'll also be in contact with plasterboards producers. Heavy metals is a problem, but also that our calcium sulfate content in our gypsum is low again. When it comes to our sulfuric acid, we are looking into if we can produce gypsum using our sulfuric acid and calcium species, because hopefully the coal-fired power plants will shut down the next 20 years, and there will be a need for calcium sulfate in the market. So hopefully we can make pure calcium sulfate from our sulfuric acid. The main challenge we see is to avoid co-precipitation of impurities along with the calcium sulfate. But I think that can be solved by doing it properly and control of the pH. So this is our view on waste valorization on fly ash compounds. Thank you very much for your attention.
Thank you, Morten. We are running a bit on overtime, but we have one question here. challenging your statement about the carbon dioxide negative process of Carbonate. I was wondering how it can be considered as carbon negative, since the capture of carbon dioxide otherwise would happen from the air.
I don't think that's completely true, because when you look at fly ash over time, the pH is lowering, but the main mechanism I don't believe is CO2 capture. These other mechanisms. I believe it's pozzolan effects you see that in fly ash. That's the reason why pH is dropping. That's at least what we do.
And I guess another one would be that you are not exposing your fly ash to air in that extent or for that long periods of time either, so it would fully have time.
Yeah, it will be a long time process. Completely agree. But the pH drop in fly ash over time, some is carbonation, but the main mechanism I don't believe it's carbonation.
Yeah. Thank you.
I think we can go to the wrap up.